So let's continue with the image data and labels. Again, we have the NIST dataset, and in this case, we only select 1, 2, 3 in this dataset, and we can see with this histogram here how many digits there are of each one of them, and it seems like the 1s are overrepresented, followed by the 3s, and then on the 2s. There's a little bit of code here. In principle, I'm just extracting the indexes where we have 1, 2, and 3 in the label data set, and those are the ones that we have selected. And a problem with limited data is, as I already mentioned, is that we have few data points or limited amounts of images, which is very often, particularly if you have experiments at large-scale facilities or also in clinical studies. You don't have maybe all so many patients with the disease that you want to observe. And that makes it hard sometimes to make predictions. So you really need to get... so you can be quite limited. Another problem is unbalanced data. And there are different types of it. So in one case, you have a huge representation of something, and that's peeking out. That's really easy to detect. But very often, the thing you want to detect is this little bump within the other one. And it's not so easy to identify that because it's just gives a little bit a bias in the large histogram. So it's much harder to see it from the histogram. And examples of that are blood vessels in the body, very thin structures that goes around, roots in soil, could also be cracks in construction materials, things like that. They are very distinct things when you look at the images, but looking at the whole data set, there are very few pixels or voxels associated with them. Then, of course, you can have little or even missing training data. That can, of course, be helped. Then you have to sit down and do the whole annotation and training data preparation. So, the other cases, in this case here, maybe you select a little bit more bias towards the one that is small and hope you have still sufficient data in it. Otherwise, you train a lot on something that is not helping you. So then we come to the augmentation, which is a way to modify the images. And different ways. We could have, so we start out with a point, we have too little data, but with some geometric transformations, we can actually improve that we increase the intensity, we rotate, we move around, changing colors, shearing it, and we can also, to add on, it's noise to the data, different signal-to-noise ratio. Can also add blurring to simulate different acquisition conditions, different resolutions. So all this is what with your data. So here is one example. It's retina images where you have an original picture here, and then the label image looks like this. And then we have some elastic deformation, so every grid piece is moving around. Then it's slightly changed here. Rotation by 30 degrees or zooming a bit in different directions. And this was part of a master project by a student of mine. Actually, the target was to look at root structures, but the retina images was a good data, so I used that instead. Then the limitations is you cannot do all modifications. So, for example, You cannot flip the ACT image because then you are not really representing the same anatomy that you were looking at. The values that you see in the image in a CT image still must have a physical meaning. Say that you have Hounsfield units of 30,000 all of a sudden will not make sense. Also shifting the bias, so the 0 in Hounsfield units is corresponding to water, I think. And that should remain on the 0, otherwise you're not training the right thing. So on CT images, in particular in medicine, you cannot move around too much. And so scaling these parameters also change the interpretation. So be careful with how you distort the images. Also, how much geometric distortion can you allow yourself? I mean, an underarm which is 3 times longer than the overarm is realistic. So you need to have scaling that makes sense. So the distortion must be within some natural bounds, otherwise there is no point in it. This is the help page of Kera's data generator. So that actually a tool that is the machine learning API called Keras. And here you can a bunch of pictures or images of some kind. A collection of parameters that you can play with and set boundaries on how much you want to change them. And you say you want 10 images from this, and then you get an data set. And playing with this can be done. There is a demonstration how to use it on this. Yeah. So if you want to look into more how to use that, there is the link. And here is an example how we can set it up. A little bit more easy to see than the help page. So here we can see that we have feature-wise center, sample-wise center, some whitening, ZCA, I don't actually know what it is. Rotation range, so that means we can do plus minus 30 degrees. Width change also within some boundaries, and so on. So you can really see here you can which parameters you can play with. And that where we take again the data set from MNIST and setting up the augmentation. So here we produce, train the whole augmentator, and then we get all the images from this piece here. And then we get batches, and the output of this is, let's see, I just need to, hello. Here you can see how the output is from this augmentation, and you can see first this 2, how it moves around, it's a little bit rotated. The 0 is also, and that's also a thing you may have to look out for when you do this augmentation. Do you want the object to stay within the bounds of the image? Because here it's actually moving out of the edges or not. That's something you have to watch out for or decide if you can accept. Then we can look at the larger and that can also be modified in a similar way. And then we get images, again, I need to move up. The same principle where we have this augmenter fit, and then we run it stepwise, getting different label batches. And here you can see, in some cases, then the augmentation makes sense. Other cases, you can ask yourself what it's about at all here. So, for example, this one or that one doesn't really make sense. So the question is, I use it. So in this case, I think the parameters were set a bit too generous. And that is something you have to critically observe when you use this augmenter. Does it really represent what I want? A baseline is a simple, very easily implemented and understood model for doing the analysis. And it should, in a way, the problem you have, and could also represent a worst case scenario for some kind of augmentation learning algorithm. And why do we need it? For example, we have here a base model example, and you have a model that is actually accurate to more than 99%. And that is for predicting breast cancer. And the predictor is, do I have breast cancer? You add age, weight, race, and say the answer is no. It's actually really good, because if you look here, the incidence is 89 out of 100,000 women. That means 0.09%. Fantastic, isn't it? Problem is, it actually to see this little detail, but we can use this kind of algorithm as reference when we implement something else. Just saying no. And that is where the baseline comes, that we at least want to do this. It can also be random guess as a baseline. Yes, no. Probability is also a possibility, but it's in principle very easy and quick to calculate. So a dummy classifier that is available in scikit-learn is has different strategies. In this case, I have selected strategy most frequent. And then we have some data set here where we have different persons. And we say it's healthy, healthy, healthy cancer. And we have trained this basic classifier to do this. And the output is that if we take this prediction, it says everything is healthy. It's healthy for 0, it's healthy for 1, which we would expect. Also for 2, I don't have here. For 3, it's also healthy because we have the most frequent, and that takes the majority as the predictor. And if we would put in 100 in this, it would also say that it is healthy. So this value here is probably some kind of metric of something, which I don't know actually. It's just hypothetical case to demonstrate. Looking at the dummy classifier on the MNIST data, then we have again our numbers. You can see here we have the digit distribution 0, 1, 2, and up to 9. And what the dummy classifier would do here, maybe some of you can tell me, what you expect happens here if you use the same dummy classifier as I used for the cancer case before. If you look at the, yes?
Always say it's a 1.
Yep. This is what's happened. And I don't think there is more on this slide, so let's train the model with most frequent. And yeah, as you said, the basic test, we take in 10 images, and it tells us all digits are 1. So that's the effect of using this. And it's of course not a very good model, but it's at least something to start with. And there are other models like calculating the average value of the images. It's actually a little bit better because the average value reflects a little bit the area of the labeled material. So anyway, here you can see when we print it out, you can see here that it's everything except the ones are red. So we actually do right sometimes, but mostly. It's actually already told. So the reason is now we have the histogram looking at the representation of ones, which is going to be our majority. Another baseline would be nearest neighbor. That's an algorithm that we are going to talk about in some weeks. But in principle, what it does is it computes. It looks. You have a point here in some into the feature vectors. You see that this point, and looking for the nearest neighbor around this point, and you conclude that okay, it's the closest one is in the blue class. So let's say it's blue. If you have a point in here, you can say that okay, it's the closest one is in the red, and then you say it's a red class. And the nearest neighbor can also say that you can also use it with several neighbors. So if you are like in say this area here, and say you have very many neighbors, so say we have 5 neighbors, then you will look and you come to the conclusion that it's actually a blue point because there are more neighbors in this that are closer from the blue than from the red. So you can tune it a little bit on that. And here is another case where you have many more dots and also more neighbors, and then you can get more fine-grained around. So let's try again using neighbor data. We have loaded now, and training. So we use this and running up. Now we have only one neighbor in this training. And now the prediction is quite good, actually. And to be honest, it's extremely good because we predict all the same. And now I didn't. Maybe someone. Why did this perform so well? The question lies in what did I use for the training and what did I use when I want to predict? The same, exactly. And that makes the nearest neighbor perfect match. Yay, we predict the right thing all the time. So what you need to do when you you test your algorithm is that you really need to take a different data set. Otherwise, you do a perfect match. And if we do that, we can see that it doesn't perform anymore. Quite good, but not so well. So now we have more or less a 50-50 chance of doing right in this data set. And it's also actually predicting something else than just once. So here it actually predicts a 3. This one it thought was also 1, but it isn't. This one is also kind of predicted to be a 1. Looks like a 1, kind of, but anyway. So this is something you have to watch out for when you work with any kind of training, that you never test with the same data as you used for training. Then we start needing some kind of metrics to define how good are we actually. And is a so-called confusion matrix. And in that we have on the y-axis we have actual true, so that is what we have labeled it to be. And on the x-axis we have the predicted true and false. And the diagonal is what we want to have, where we want to have the most values. And this diagonal is to be minimized. So the more we have along the top right to left diagonal, the worse we perform. And if we look at for this data set, we can see that we have a good centering around this main diagonal, but there are also some outliers. In some cases it has problem, like for example the 5 here. can be misinterpreted as a 3 or also as a 6. Down here we have the 8, which is mistaken by being a 1 or a 3. The 3 is quite natural. The 1 I don't really understand, but apparently it goes that way. 7 naturally goes towards the 1, but apparently also to the 9. So sloppy 9 may look like a 7, so kind of makes sense. But you can anyway see here pattern in how different classifications work. So it's a good tool to analyze how well you perform. This is now a more technical part. So we have talked about using all these data sets, and they are mostly stored in some kind of data frame or in or some database. And if you bring the database into the computer in the Python workflow, then we are often talking about some kind of data frame, and that's kind of a spreadsheet, a mix between a spreadsheet and a database. And you can use it for one is in it. You can also put different metrics or measurements you measured. And so it's a quite good tool, useful tool to work with. And in Python, you can do it different ways. You could actually have one array, but use dictionaries or some kind of structure. And things we want to operate on these feature data in the images are maybe counting, statistics, selection, transformations of some kind, and also visualization of the results. And let's see. Oh, there is a problem here with the different storage types. We can have a problem to implement these functions. Particularly if you work with a lot of arrays, it's starting to get very confusing. What is that array? And also nomenclature. And it's also a problem with flexibility in it. And with the solution now is using these data frames. So a data frame is a data container, columns and rows mainly. Very similar to a spreadsheet table. And all the data in columns. And the good thing is you can also do filtering for selections. You can sort in the rows of these columns. You can perform arithmetics between different columns. Can also compute statistics and read and store data into different databases. So recently I just had a spreadsheet that I loaded into a data frame, and then I could manipulate that. You can also work with a SQL database if you like that, or any online database probably too. There are different reader or data fetching interfaces in Pandas. And Pandas is the package that we are going to use. First thing when we create a data frame is we have to import Pandas. And you can create it from different sources, from a dictionary. You can import it from a data file, or you can also take it from a NumPy array. But the first step that we need to do is to import Pandas. So that was done. And then we go on. And one way of doing it is reading a spreadsheet. In this case, as comma-separated values. And we have PD stands for pandas dot read CSV. You can also do read XLS and other formats. This table has something of hours that you will see in some weeks. If we look at the red data, then we execute this cell, and you can see that we have a lot of parameters, which probably makes sense to a biologist, but not to me. Anyway, we have a lot of parameters here that we want to look at and do analysis on. And to save it, works a similar way. Then you just take here this data frame, which we called Pheno, and write to CSV. And then you just type enter here, and we have created a new CSV file with our data frame. We can also create a data frame using dictionaries. And in this case, I create a data frame with position, which is the eye of this loop, and a sinus value. So it's just the NP sign. And in the dictionary, we have a position and sign column. And executing this gives us something like this. And then we need to execute it. So we have this dictionary that we bring into there. So we have the dictionary that we bring into create as a data frame, and then we have a DF. And now we can look at what that looks like. Yeah, there we have our little table with position and design. NumPy arrays. You saw before, we created dictionary labels for each row in the data. It's maybe not so efficient. So we can also create the dictionary in a way that we have a position entry, which takes a vector, and a sign entry, which takes a vector. So this may be easier to work with, mostly. And that gives us the same kind of vector. And now we have these columns and we want to do something out of them. For example, we realize we want to create a cosine column too. And to do that, very easy actually, you just say data frame and give the label of the new column. You don't have to tell you create it. You just say you want something with this label, and that is created using the cosine of the data frame column called position. That we have created a new column in the data. Of the column sine and cosine, and bring that into the sum column. The last one is a little bit more fun, because here we can do some verification. So we see everyone that is positive is going to be true, and the other ones will be false. And the test is just that we have the data frame column of sine greater than 0. Execute this and see what it looks like. Yeah. So we got 3 new columns, 2 with values, and the last one with just a boolean. And that indicates you can have different types of value in these columns. You can not only have values, booleans, but you can also have text. You can have images, if you like. Not too big, because that will blow up the memory, but you can have it. But in principle, then you could have a labeled image. An image, it's labeling, and also some annotations what it is in different columns. And then you have a nice collection of information. A very strong, good thing about these data frames is that you can also do content filtering, saying that you want to create a new data frame based on the one we had with the signs, but we will only take those that fulfill this criterion, and then we look at what that data frame looks like. And I think we should actually add, oops. That one. 5 means it takes the first 5 in the data frame. And here we have it. And now you can see, as we expected, only positive anything in the selection criteria. And this column also confirms it's positive, because this one was actually checking if the value is positive of the sign. Then we can, if we realize, oh, the column names I used were, so I want to rename them. So we have first our data frame here, which is, we have the names A and B. And A and B doesn't tell anything, so we want to rename these columns, and then we have this renaming function. Then we say that the columns called A are renamed to Hey, and the ones called B, they are going to be called Hop. So let's run it. And yeah, as expected, we have now renamed our columns. Calculations, we already did column-wise calculations, but now we want to look at also statistical information from these data frames, and we can compute the average value, we can compute standard deviation, minimum, maximum, and median from the data frame, and that gives us a very nice collection of information where you see you have the position. Doesn't make sense actually to compute the average of it, but anyway, we got it. Then we have the sine, we have cosine, and so on. And actually we get also interesting, the Booleans also computes an average, but that is actually Boolean is 0 and 1, so it's the average of zeros and ones. Then we have if you want to look at all of these informations at the same time, and I need to go in. And here you get a little bit more information in one big chunk. Before I just looked at the average value, but if you write describe, you get all these parameters at once for each column. And that can be quite, there's a quick way of getting an idea of your data. We already looked at filtering, so you can select a different piece. Now I'm looking at the places where the sum is more than 0, and in that case I want to look at only the sign column and compute standard deviation of that. So it's, well, constructed example, but you can actually really select out information from one column and apply some operation on a different column. And executing this creates a number. I don't know if it makes sense, but right now we have this number. And then we can do quite complicated grouping by names, etc. So now we create a new group which is called positive, and we group it by the, so we group the database by the name positive and compute the mean of that. And here by that we can see that we have the positive, and it computes true false information. And you see here the average value of the sine if it's negative, the cosine if it's negative, the average value of the sum if it's negative, and so on. So you can do more advanced grouping. The variations of this are quite big, so if you want to dig deep into working with the data frames, I would recommend you to take a deep look into the manuals, which are huge web pages. But anyway, here's another one. Maybe there was too much information at once, so we can actually also reduce it a bit, and then we get something like this, and this would only apply to the sign column. And here you have the case of false and true again, if it's the sum was positive, and then you can get the average value and the variance of that. Sorry. One thing actually. And which values you compute is given by this aggregation vector, where you have mean and variance. So you can tell which operations you want to compute. And finally, to round off a little bit of plotting with these data frames, then you can actually directly plot from the data frame. So let's look here. We create some subplots, and I take the data frame and say I want to plot, and that into axis x. And it plots all the columns at once, which doesn't make sense with the position, for example, because it's just a straight line, while the other ones are sines and cosines in some way. And let's see, no, that's not continuing. Okay, then we can also do selective plotting, like we selected before. We selected a column. In this case here, I just plot the sign, and I still want to plot it in axis. In this case, I want to plot it in axis 0, and I can set also the title here. Then I can select which axis is which column used in. So here I say x goes to the sine and y go in the cosine, and that should be plotted in axis 1. And the final one is probably with some selection. Yeah, so here I select again the positive part, and I want the position here, and I want the cosine. And then you can see what that looks like. I thought we could switch it up, but I couldn't. Anyway, we don't have very many data points, so the sine is quite coarse. If we plot sine and cosine against each other, we should expect a circle, and that is also what we get. And then here is the filtered one, where the cosine is selected when the sine is positive. Plotting styles, you can not only... Yes?
I have a question regarding the previous slide,
Yeah.
also the previous one. When do you define like the AX? Like also the previous one?
Yes. Sorry. Let's go back to the previous one. That's smaller. So what I do is I say here the PLT subplots. I say I want one row and one column and the fig size, and the output of subplots is a fig and the axis. So the axis is a vector or array or a scalar depending on the kind of matrix I defined here. So I could have, for example, 2 by 2 rows and 3 columns. Then I would get a 2-dimensional axis. If I, in this case, I only get a scalar, and that's why I can put it up here like just x equal x. And in this case, I use 1 row and 3 columns, and then all of a sudden I need to put an index here on the x. There are different ways of, I think there are 3 different, quite many ways, let's put it like of how you can do sub-panels in Matplotlib. This is the one I usually take. It's quite strict, so it's always the same distances between everything. With other arrangements, you can define one plot is larger than the other one, and so on. So you can also add some dimension parameter here back on the subplot. But what I usually do, you don't see it here, but if I had multiple rows, then you have a 2D array, and that's sometimes inconvenient if you do a loop to go through all the panels. And then I use a command called ravel, and you will see that if you look into my visualization code in my slides. Until now, we only showed different plots, line plots, but you can also do very many different kinds of plots. For example, here I selected bar plot. You can also do scatter plot, pie charts, yeah, and many other kinds. That is in the Pandas visualization documentation. There you can see the full list of different ways to produce this. And if we look at the output, here you see the data and also the scatter plot, where you can better see the circle. The other one was a little bit overlapped, so it wasn't so nice. Depending on what your purpose is, you can also the data in different styles. And I think I'll skip this one. It gets quite messy and complicated, but you can have it if you would need to do set operations, combine different data frames. This part would be showing how to do that, but I think I skip it today. But I want to come back to this frame where you really want to use these data frames and where is it useful. And looking at the data size, you see here, if you have the raw images, you have a lot of data. Segment is maybe a little bit more, feature data, statistics, and model. And also the level of abstraction increases when you go in this direction. I would say mainly I would use the data frames in this part, but occasionally in that part, because I think mainly having images or separate images are mostly more efficient having them in a large array or something like that. And if you have really large data, you can also go for something called data frames, and they can also handle data on the disk, so you can just fill it in when you need it. Here in the Pandas, you need to load all the data in your memory, and that is quite often limited. Larger data sets, then I would say go for the Dask data frames instead. They will have essentially the same syntax, so it's the same look and feel when you work with it, but you have the thing that the hard drive is actually the storage. Yes, and that was end of today's lecture. And today we looked at different types of data sets, not only your own, or mainly not your own, but hopefully you could see that it is useful to use someone else's data, in particular if it's labeled and already prepared, because it helps you to get started with your work. Preparing the data is something that is time-consuming, but necessary, and in particular, it's important to do it with high quality, because the rest of your conclusions will actually depend on how well you prepare your data. And if you have too little data, then you can work with the augmentation, stretch and pull the data in different ways. And when you start developing your algorithms, it's a good idea to have a baseline to know how good am I at all. Is the random guess actually beating my algorithm, or am I better? And then we can try different algorithms. We looked at the majority choice, the most frequent, and we also looked at the nearest neighbor as a baseline. The performance can be checked out with a confusion matrix, and then we went into looking at data frames and how you can use them to store your data when you start extracting information. Yeah, and that was the end of today.